Have you ever like thought about all this stuff we do online, like all the transactions and communications and stuff?
Oh, yeah.
Could all that be vulnerable in the future?
It's a question a lot of people are asking.
Yeah, that's kind of what we're diving into today. It's about quantum computing and like how it could impact, the encryption we use now.
Right now, we're mostly using ECDSA.
ECDSA.
Exactly.
Okay, so we've got this paper, and it gets into how you could actually use something called Shor's algorithm to attack ECDSA.
And they use Qiskit to actually simulate it.
Oh, wow. Qiskit, that's the quantum computing framework, right?
Yeah, it's from IBM.
Okay, cool. So if you're not like a total cryptography expert, don't worry.
Yeah, we're going to break all this down.
Yeah.
Make it clear for everybody.
So ECDSA, what does that even stand for?
It stands for Elliptic Curve Digital Signature Algorithm.
Oh, wow. Okay.
It's kind of a mouthful, but
it is, yeah.
you see it everywhere.
Yeah, it's like everywhere online, right?
Pretty much. If you're doing anything secure online, it's probably using ECDSA.
So like secure websites, online banking, even cryptocurrency.
All of that, yeah.
So it's basically like a digital signature then.
Yeah, you can think of it like that.
Okay.
Like a digital wax seal.
Oh, I like that.
So with a wax seal, it guarantees that the letter came from the right person and nobody messed with it.
Right. Nobody opened it up and changed something.
Exactly. ECDSA does the same thing, but in the digital world.
Okay, that makes sense. So how does it actually like work? What makes it so secure?
It all comes down to this really hard math problem called the elliptic curve discrete logarithm problem.
ECDLP.
Yeah, ECDLP for sure.
Okay, so that's the key to ECDSA's security.
Exactly. For a classical computer to solve ECDLP, it would be like trying to find a specific grain of sand on a massive beach.
Oh, wow. So it's pretty much impossible to crack right now.
For now, yeah. But that's where quantum computers come in.
Right, because they're not like regular computers. They use totally different principles.
Right. Quantum computers use these things called superposition and entanglement. They can tackle problems like ECDLP in a way that classical computers just can't.
So they could actually be a threat to ECDSA.
Potentially. Yeah.
It's kind of scary to think about that something that seems so unbreakable could become vulnerable.
It definitely raises some concerns.
So how could they actually do it? How could a quantum computer crack ECDSA?
The key is something called Shor's algorithm.
Shor's algorithm.
Yeah, it was developed by Peter Shor back in 1994.
Oh, wow. So this has been around for a while.
It has. And what's really interesting is it provides a kind of shortcut for solving certain math problems.
Including ECDLP.
Exactly.
So instead of searching through that whole beach for the right grain of sand,
Right.
Shor's algorithm gives quantum computers a way to find it much faster.
Yeah, like having a metal detector on the beach.
Ah, that's a much better way to find it.
Right.
Right.
Shor's algorithm lets quantum computers factor large numbers super fast.
And that's how they could break ECDSA.
Right, because factoring large numbers is directly related to solving the ECDLP.
Wow. Okay, I'm starting to see how this all fits together.
It's all connected.
So this paper we're looking at, it actually simulates a quantum attack on ECDSA using Shor's algorithm.
Yeah, and they used Qiskit to do it.
So Qiskit's like a programming language for quantum computers.
You could think of it that way. It's a framework developed by IBM.
Okay.
It lets researchers create and run these quantum algorithms.
Interesting. So they were able to simulate how Shor's algorithm could attack ECDSA.
Right. Now, keep in mind, they didn't use a real ECDSA system.
Okay.
They worked with smaller elliptic curves.
Oh, so like simplified versions.
Exactly. They had to make it manageable for the simulation.
That makes sense.
So they designed these quantum circuits in Qiskit.
Quantum circuits.
They're basically sets of instructions for quantum computers.
Okay, so they're telling the computer how to do the math.
Yeah, basically.
So it sounds like they created like a scaled down model of the attack.
That's a good way to put it.
Did they find anything interesting?
Oh, yeah, definitely. As they simulated larger and larger prime numbers, the attack got more and more complex.
Oh, so it's not as easy as just running the algorithm.
No, it takes a lot of resources.
Even for a quantum computer.
Even for a quantum computer. They actually show this in Table 2 of the paper.
Okay, so they really did a deep dive into this.
Yeah, they did.
So even if someone had a quantum computer right now and they knew how to use Shor's algorithm, they couldn't just break ECDSA.
Not real-world ECDSA. No, it's still too complex.
So there are still limitations.
For now, yes.
But this simulation, it shows what could be possible in the future.
Exactly. And that's why this research is so important.
Right.
Quantum technology is developing so fast.
Yeah, it seems like things are moving really quickly.
They are. We need to be ready for when these attacks become more feasible.
It's a little bit like a race against time then?
You could say that.
Okay, so we've got these quantum computers that could potentially crack our current encryption.
You're right.
But what can we do about it?
That's the big question.
Is there any way to protect ourselves?
There is. We're going to talk about something called quantum-resistant cryptography.
Okay, quantum-resistant cryptography. That sounds promising.
It is. It's basically the key to navigating this whole challenge.
Okay, well, let's dive into that more in part 2 of our deep dive.
Sounds good.
We'll see you then?
Yeah. Ha.
Okay, so we were talking about quantum-resistant cryptography.
Right.
So is that like our, silver bullet against this quantum threat?
Well, it's not really about creating something unbreakable. You can't really do that.
Right.
It's more about designing algorithms that are totally different from what we use today.
Okay, so algorithms that quantum computers can't crack.
Exactly. They need to be resistant to attacks from both classical and quantum computers.
So instead of building a higher wall,
Right.
we're changing the whole game.
Exactly. We need a different approach.
Okay, so I get that.
Yeah.
But are these quantum-resistant algorithms, like, real? Or are they just theoretical?
Oh, no, there's a lot of work happening in this area.
Oh, really?
Yeah, there's actually a competition going on right now.
A company?
Yeah, it's run by NIST, the National Institute of Standards and Technology.
Wow, so they're trying to find the best quantum-resistant algorithms.
Exactly. They've got submissions from experts all over the world.
That's pretty cool.
It is. They're evaluating them, testing them,
Yeah.
trying to find the most promising ones.
So it's like a real race to find the best solution.
Yeah, you could say that.
So NIST is going to pick a winner, or maybe a few winners,
Right.
and then we'll all switch over to those new algorithms.
It's not quite that simple.
Uh,
It's a huge undertaking to transition to quantum-resistant cryptography.
I can imagine.
It's not just about swapping out one algorithm for another.
Yeah, we're talking about changing, like, the whole foundation of online security.
Exactly. Think about all the systems that rely on encryption.
Like everything.
Pretty much everything: online banking, communications, critical infrastructure.
It's a lot.
It is. We need to update software, hardware protocols.
So it's not going to be easy.
Definitely not. It's
Yeah.
a massive logistical challenge.
Where do we even begin?
Well, we have to start planning now.
Okay.
We can't wait until quantum computers are powerful enough to break our current encryption.
Right, we have to be proactive.
Exactly.
So what are some of the biggest hurdles? Is it just a matter of, like, finding the right algorithms?
It's more than that. We need to make sure those algorithms are truly secure.
Right, because we're dealing with a whole new kind of threat.
Exactly. We need to be really sure that these new algorithms can withstand attacks from quantum computers.
So how do we do that?
Lots of testing, analysis, scrutiny from the cryptography community.
They're really putting these algorithms through the ringer.
They have to. We need to find any weaknesses.
So it's like a constant back and forth.
It is. It's like a game of cat and mouse.
So there are those security challenges, and then there are the logistical challenges too.
Right. We
Yeah.
have to think about all the devices that use encryption.
Like computers and smartphones and everything.
All of that. And we need to update them all.
That's a lot of devices.
It is. It's going to require a lot of coordination across different industries and governments.
Okay, so it's a huge task.
It is. But it's essential if we want to maintain security in a world with quantum computers.
It's not just about protecting data either, right?
Right.
It's about trust and stability.
The whole digital infrastructure.
Exactly.
What are the implications if we don't make this transition?
It could be really disruptive.
In what way?
Think about financial markets, communications networks, national security.
If our encryption is compromised, all those things could be affected.
Absolutely.
Okay, so I'm really starting to understand the urgency here.
It's important to take this seriously.
So what can our listeners do? How can they prepare for this quantum future?
The most important thing is to stay informed.
Okay.
Learn about quantum computing and what it means for cryptography.
Right.
There are a lot of resources available online and through educational institutions.
We can share some links in the show notes.
That's a great idea.
Yeah.
And support organizations that are working on these quantum-resistant solutions.
Okay, so be informed and be supportive.
Exactly.
It sounds like we're all in this together.
Yeah.
This is a challenge for everyone.
So this is an ongoing story, right?
It is. The
Yeah.
field is constantly evolving.
So we're going to have to keep learning and adapting.
Exactly.
It's not just a technical challenge either, right?
It's a societal challenge.
We need to work together to make sure this technology is used responsibly.
Absolutely.
Well said.
It's up to all of us to shape the quantum future.
So we've talked about the threat of quantum computers
Right.
and the race to develop quantum-resistant cryptography.
Right.
But how will this affect society as a whole?
That's a big question.
There's so many possibilities and so many challenges.
It's an exciting time.
It really is. We're going to dive into all that more in the final part of our deep dive.
Sounds good.
Okay, so we've talked about Quantum computers, breaking encryption and all that,
Right.
the race to make, quantum-resistant algorithms and stuff.
Right.
But quantum computing, it's not just about that, is it? It seems way bigger.
Yeah, it's definitely bigger than just code breaking. It could change a lot of things.
Like what kind of things?
Well, think about medicine.
Okay.
Quantum computers could be used to design new drugs and therapies.
Oh, wow. So like really targeted treatments.
Exactly. We could see breakthroughs in treating diseases that we can't cure right now.
That would be incredible.
It would. And it's not just medicine, material science, too.
What about materials science?
We could discover and develop completely new materials.
Oh, wow.
Things with properties we've never seen before. Lighter, stronger, more efficient.
So we're talking about like a whole new era of materials.
Pretty much. It could revolutionize industries like energy transportation, even space exploration.
It really does feel like we're on the verge of something huge.
Yeah, the potential is massive.
But with all this potential, there must be some concerns too, right?
Oh, definitely. There are always concerns with new technology.
Like what?
Well, one of the biggest ones is ethics.
Ethics.
Yeah, like who's going to have access to these quantum computers?
Right, because they're probably going to be really expensive and complex.
Exactly. So will there be a quantum divide?
A quantum divide.
Yeah, between the people who benefit from this technology and those who don't.
That's a really good point. It's like the digital divide, but on a whole other level.
Exactly. And then there are the security concerns.
We already talked about breaking encryption.
Right, but what about other malicious uses?
Like what?
What if someone uses quantum computers to develop new weapons?
Oh, wow.
Or to disrupt critical infrastructure? These are things we have to think about.
So it's kind of like a double-edged sword.
It is incredible. Potential for good, but also potential for harm.
Yeah, every new technology seems to come with those kinds of risks.
It's true. That's why it's so important to talk about these issues now.
Right before it's too late.
Exactly. We need to establish ethical guidelines, regulations, safeguards.
So we can make sure this technology is used responsibly.
Right, for the benefit of humanity.
Okay. I'm definitely seeing the bigger picture now.
It's important to think about these things.
So if we can harness this power responsibly,
Right.
we can create a truly amazing future.
We absolutely could.
So what's the takeaway for our listeners? What should they be thinking about?
I think the most important thing is to remember that quantum computing is a paradigm shift. It's not just a new technology, it's a whole new way of thinking.
So we need to stay informed.
Yes, definitely. Learn about quantum computing and how it's going to affect our lives.
Stay curious.
Exactly. And get involved in these conversations.
Because the quantum future is being shaped right now.
It is.
And we all have a role to play.
Well said. So that brings us to the end of our deep dive into the world of quantum computing.
It's been a fascinating journey.
It really has. We've explored the potential threats and the incredible possibilities.
And the challenges ahead.
If quantum computers can break today's codes, what kind of encryption will we need for tomorrow?
It's a question we all need to be asking.
What other mind-boggling possibilities and challenges are waiting for us?
Only time will tell.
Well, we hope you've enjoyed exploring these ideas with us, and we'll see you on our next deep dive.